Not me, Kuba Zakrzewski.
Kuba Zakrzewski was assigned to make a viewpoint and he consulted Krzysztof Sacha and he said got information for the world to learn about crystals.
Thank you. Thank you for the invitation and for kind introduction. So I'm going to tell you about time crystals. And my talk will be divided in two parts. In the first part, I will try to explain you what is the formation of time crystals, and in the other part, I will consider condensed matter physics in time crystals. So that will be somehow separated parts. So first, formation of crystals. And let me start with something which we all know quite well, with space crystals and the formation of space crystals. If we have solid state Hamiltonian, the solid state Hamiltonian is invariant under translation of all particles by the same vector. So that means that the system eigenstates must be also eigenstates of the corresponding space translational operator. And from that we can easily draw the conclusion that if we prepare the solid state system in the ground state or in any eigenstate, and if we calculate the single particle probability density, so this is a probability to measure a single electron or a single nucleus, such a probability has to be constant in space. At that one can ask, where is the space crystal? And space crystal emerges due to the spontaneous breaking of space translational symmetry. And this is so because the ground state of the system is strongly vulnerable to any perturbation, and it is sufficient to measure only a single particle, the position of a single particle, and then the probability for the detection of next particles starts revealing periodic structure in space. So that because it happens under any perturbation, this process is called spontaneous breaking of the initial continuous time, the space translational symmetry, into a discrete space translational symmetry. So that's the formation of space crystals. And in order to switch to time crystals, what we have to do, we have to basically exchange these two quantities, time and space. We will see that what we have to do...
In the real physics, in the real crystal, it's not true. Because in addition to the translation symmetry, the crystals possess the rotation symmetry. And the important part is that both rotation and translation symmetries have to somehow coincide.
If you...
There is a cohabitation
yes,
of those two symmetries, and that's why we only have 32 classes of crystals. Otherwise, we would have infinite number of possible crystals, and we have only finite
yes,
number.
in the simplest, I would like to make things as simple as possible. What we...
So it's 1D.
For example, in 1D, in 3D, you can break...
In 1D, there are no crystals whatsoever.
Yes, but...
there is a proof in the number which is booked in the one dimension there are no crystals.
But I think that one sentence was a bit too strong. I think that it's not enough to measure or to break the symmetry by detecting single atom. And if you allow for because then you look for two-body correlation function and you will see some finger oscillations only.
No, if you have long-range interactions, this is not true, because then you will see the crystal structure. That's of course that not every solid-state physics can reveal crystalline structure, but apart from the details, I had in mind that the system which reveals crystalline structure, but still the symmetry the translational symmetry has to be spontaneously broken.
Could you please repeat what's plotted on the right?
Okay. We have many body system, solid state system, and then we have many body wave function. We can calculate the n. For example, if we have n particles, we can calculate the n body probability density. But also we can yes, but then we can integrate this probability over all particles but one, and ask what is the probability for the detection of a single particle. That's the probability for the detection of the single particle before the symmetry breaking, and this is after the symmetry breaking.
So the same single particle density.
This is the same, but the state is this is the same quantity, but the states they correspond to are different. Now, coming back to time crystals. In time crystals, what we will have to do, we will have to exchange these two quantities, because here we fix time at the moment in the measurement and ask about the properties of the system versus space. In time crystals, we will fix the space point and ask how the system behaves as a function of time.
So any periodic system is a crystal?
Not really, because what we are looking for many-body system, which, as we analyze the Hamiltonian, this Hamiltonian possesses continuous time translation symmetry, but it turns out that eigenstate of this system are strongly vulnerable to any perturbation, and spontaneous process, but this time spontaneous breaking of time translation symmetry can be predicted. I'm going to do this too. So now let us consider time-independent system. And time-independent system, Hamiltonian of the time-independent system commutes with time translational operator, because this time translation operator is simply the evolution operator. And from that property, we can, of course, draw the conclusion that if we fix the position in the configuration space and ask how the probability for the detection of our system at this space point changes in time, if the system is prepared in an eigenstate, of course, this probability doesn't change because it is simply the stationary state. However, in 2012, Wilczek proposed many-body system, which even if it was prepared in the ground state, it was supposed to be strongly vulnerable to any perturbation, and any perturbation was expected to push the system to periodic motion. In other words, a spontaneous process was expected where the continuous initial continuous time translational symmetry can be broken into a discrete time translational symmetry. And shortly after this publication, it was proven that such a situation is not possible if the system is prepared in the ground state. It turns out that it can, in the Wilczek model, it can happen if the system is prepared in some excited states. But probably I will not have time to talk about this problem. Maybe if I will return to this problem. But I would like to tell you about something different. I would like to show you that the different kind of spontaneous breaking of time translational symmetry is possible. I will show you that the breaking of the discrete time translation symmetry into another discrete time translational symmetry is possible. So that basically is the first part of my talk. Yes, this is period. One can say it is period doubling, but at the bottom of this process is a many-body physics and the spontaneous breaking of time translational symmetry. Of course, it reduces at the end to the simple results. But okay.
So if I were build a mechanical system,
yes,
and two pendulums suspended on a rope, which is slowing it down, period down, would I be allowed to call it a time crystal?
now you will see that I wouldn't. But let me show. You will see. So the
So far, this example, I don't know.
no. So let me illustrate this with a simple, that it is possible with a simple system. I'm going to consider many particles bouncing on an oscillating mirror in the presence of the gravitational field. But first, let me introduce as a simple element of this model a single particle bouncing of an oscillating mirror. And let me start with the classical mechanics. If we have a classical particle that bounces on the suppose that initially the mirror doesn't move, so we have a fixed mirror. So the classical trajectory is of course a periodic orbit. With the period, the longer the higher energy of the particle. When we turn on the mirror oscillations, of course the motion becomes irregular, but some periodic orbits survive, and these are resonant orbits. For example, there is 1-to-1 resonant orbit where the particle, the period of the motion of a particle is equal to the period of the mirror oscillations. There is 2-to-1 resonant orbit when the period of the motion is twice longer than the period of the mirror oscillations, and so on.
So that's the trick used by the basketball players.
One can say, but the mirror is then
The mirror is the hand, but that exactly.
one. Or the, let's say a taboo.
Problem in the quantum mechanics.
Or it is better to say about ping pong players.
Or the ping-pong player, whatever.
Yes. Even
That's the same. Whether you
Yes.
move this way or that way, it's the same. And the quantum mechanical, I believe it was solved in the 30s by Fermi. This is the Fermi problem, which is then used by the Fermi acceleration.
not precisely, not this probably problem. There are of course there are related problems of resonant motion. That's true. This is studied for years. But that's a classical mechanism. Now that let us switch to the quantum mechanics, and generally it is more convenient if we describe the system not in the laboratory frame, but in the frame moving with the mirror. Then the mirror is fixed by the gravitational constant starts depending on time. But now the quantum mechanics. Of course, in quantum description, we cannot look for the energy eigenstate because the energy is not conserved. However, due to the periodicity of the perturbation, we can find a kind of stationary states which are so-called Floquet states, and which are eigenstate of the so-called Floquet Hamiltonian. And this Floquet Hamiltonian is simply nearly the energy, but supplemented with this differential operation with respect to time. All eigenstate of this Floquet Hamiltonian are periodic with the period of the mirror oscillations. The corresponding eigenvalues are called quasi-energy of the system, and it is in full analogy to the solid state physics and to the Bloch theorem. But now we have periodicity not in space, but in time. There are many different Floquet eigenstates of our problem, but some of them are quite interesting because they are represented by localized wave packets that are moving along classical resonant orbits. And for example, there is Floquet state which is represented by a localized wave packet moving along 1-to-1 resonant orbit. There are Floquet states which are represented by the localized wave packets moving along 2-to-1 resonant orbits. And this 2-to-1 resonant case is slightly more complicated. Because if we think that a single localized wave packet moving along such 2-to-1 resonant orbit can fulfill conditions to be a Floquet state, it is not true, because such a motion is related to the period twice longer than the period of the mirror oscillations. However, superpositions of such two localized wave packets, which each of them moves with the period twice longer, but after each period of the evolution they exchange their role, does the job. And here there is an example of such a state. This is a Floquet state corresponding to 2-to-1 resonant orbit. Initially we have these two wave packets overlap, but because they are moving in the opposite direction, you can see interference fringes. So you can see that one of the wave packets approaches the mirror, where the mirror is located at z equals 0, bounces off the mirror and returns. The other wave packet approaches the classical turning point and also returns. And after the period of the mirror oscillation, we return to the initial situation. But now, two localized wave packets can form actually two orthogonal superpositions. So that is why we may expect two such wave Floquet states, which are represented by such wave packets moving along 2-to-1 resonant orbits. And indeed, there are two such Floquet states. They correspond to nearly the same quasi-energy. There is small splitting which can be related to the tunneling process.
Related to what?
To tunneling process. Now, that physics is actually related to the so-called non-spreading wave packets physics, which is known for a while. And actually, Trojan wave packets discovered by Professor Białnicki initiated this research in that direction. There is a good review which I would like to recommend on that physics. So this is a non-spreading wave packet and single particle problem. And now let me switch to many-body problem. Now let us consider that we don't have a single particle bouncing off the oscillating mirror, but many particles. We can think we have ultra-cold atoms bouncing on an oscillating mirror. We assume that particles are bosons. They interact via contact potential, and the interactions, we assume that the interactions are attractive. If we rest in the description of this many-body system.
Like bouncing, there was elastic collisions.
Yes, exactly.
What is concerned?
The moment, not the direction, but the value of the momentum. During the each bounces change the direction of the momentum, but not the value. That's now, if in the description of the system we restrict ourselves to the Hilbert subspace that is spanned by this two localized wave packet moving along 2 to 1 resonant orbit, then the many-body Floquet Hamiltonian can be reduced to the two-mode problem. So what we are doing, we are assuming that all physics we are interested in happens in this Hilbert subspace. And now, ground state of this Hamiltonian correspond, if the interactions are negligible, the ground state of this Hamiltonian corresponds to the Floquet state, which has properties very similar to the single Floquet state for the single particle, which I have described in the previous slide. Because each particle occupies the same single particle state, and the single particle state is a single Floquet state. And actually nothing interesting happens. However, if the attractive interactions, the strength of attractive interactions increases, if it is stronger than some critical value, a very special many-bodies ground state of this Hamiltonian is formed. And it is so because if the attractive interactions is sufficiently strong, it is energetically favorable to group all particles in the same localized wave packet. Then the many-body eigenstate of this ground state of this Hamiltonian has a structure of the Schrödinger cat-like state, where we have all particles occupy one of the localized wave packet, plus all particles occupy the other localized wave packet. The evolution of this Floquet many-body state, of course, fulfill the original time translational symmetry. That means that the evolution is with the period of the mirror oscillations. However, such a state is Schrödinger cat-like state, so it is vulnerable to any perturbation, and it is this evolution is depicted actually here, whereas there is a single particle probability density corresponding to this Floquet state, and you can see that the period of the evolution is indeed equal to the period of the mirror oscillation. Now, such a state is strongly vulnerable to any perturbation, and it is sufficient to measure the position of one of the particle, and then our state immediately collapses to one of the state which form the superposition, depending on the result of the measurement. And starting from this point,
So the number of particles is not concerned.
Yeah, because one was detected. That was
one was detected. If we detect the position, then of course the momentum is totally undefined, and we can say it is gone.
So detection Amsterdam's models detect the symmetry by detecting.
Yes, yes, that's true. But actually, it is not. It cannot be avoided, because if we want to know if the symmetry is broken, we have to perform measurement, and that immediately involves the breaking of the symmetry. Now, starting from this moment, the evolution of such state or this state takes place with the period twice longer than the period of the mirror oscillations, and this evolution is robust. Even if we perform subsequent measurement of some fraction of position of atoms, we still observe that the period is twice longer than the period of the mirror oscillations. And one can, of course, also ask what is the lifetime of this symmetry broken state, and this lifetime increases to infinity in the limit when the particle numbers goes to infinity by the product of the scattering lengths and the number of particles is fixed. So that's the illustration that the process of spontaneous breaking of time translational symmetry is possible. In other words, we can say that we have a many-body system, and due to the mutual interaction between particles, the system self-reorganizes its motion and start moving with the period which is different from the period which we can expect from the symmetry. And that result was published in 2015, and it was not, they were not noticed, of course, and it took 1 year to rediscover the same phenomenon but in different systems, in spin systems. And actually this phenomenon was realized experimentally by 2 groups and published in Nature magazine in March. And now I'm going to describe shortly the results of these two experiments. So, in the group of Chris Monroe from University of Maryland, they dealt with chain of ions. In the Mikhail Lukin group in Harvard University, they had nitrogen impurities in diamond. In both experiments, effectively the spin system was realized, and this spin system was periodically driven, and the driving consisted of a few stages. In the first stage there was a spin flipping. That was the first. In the second stage they turn on the interaction between spins, and the third stage they turn on the external disorder. And this procedure was repeated periodically. Now, if we consider, if we ask about Floquet eigenstates of this system, there are Schrödinger-Cat-like states. For example, there can be a superposition of all spins up plus all spins down, because such a state is not changed by the spin flipping. The spin flipping can only add some global phase. But such a Schrödinger-Cat-like state is of course strongly vulnerable to any perturbation, and it is sufficient to measure the direction of one of the spin, and then the system collapses immediately to one of this state. And starting from this point, the evolution is not with the period of the external driving, but with the twice longer period, because 2 spin flips are necessary to return to the initial situation. So that's a theoretical analysis of this system, but experiments were performed in 2 versions. In the first version, they turn off the interaction and turn off the disorder, and they introduce small detuning in the spin flipping. So now the spin flipping is not perfectly by pi, but slightly less. So if we perform such a spin flipping, we can imagine that what we can expect beating in the spin magnetization signal, and that was observed. But now, then they turn on the interaction, but they don't change the detuning. And even so there was detuning. Due to the interaction between particles, the system self-organized its motion and started moving with the period twice longer than the period of the mirror oscillations. And so that's this evolution was robust even in the presence of the external disorder. And that's a demonstration that the self-organization in time evolution is possible due to the interaction between particles. So that's basically all concerning the first part. And now let me switch to the second part, which is a condensed matter physics in time crystals. I would like you to really consider these two parts quite separately, because otherwise there will be some confusion. So now let me even forget about the first part. Now let us start from the very beginning.
Can I ask something?
Sure.
Because conventional spontaneous symmetry breaking, there's always a remnant, right? This, like in particle physics, we call it Goldstone bosons. There will be phonons in crystal, which somehow.
If the symmetry broken is continued, then
Yes.
there is a gold boson.
Yes.
It's not the same thing.
Why? I always thought that time is a continuous variable.
No, but
the problem is that the interactions.
But the symmetry of the Hamiltonian is discrete here.
Discrete, that's the point. The time is continuous, but this is not the discrete time. This is not the continuous time Hamiltonian. It's bim, 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 bim.
we'll,
So you are breaking bim, bim, bim symmetry, and then there is no boson theorem.
okay, that's maybe we will return to this. Condensed matter physics. So if in solid state physics, it is usually assumed that the space crystal is already formed, and the formation of the crystal is not considered quantum mechanically, because this is strongly vulnerable Schrödinger cats-like state, whatever. So it usually in the solid state physics we start with the already formed space crystal, and properties of space crystal are usually modeled with the help of the space periodic Hamiltonians. Now we can ask, of course, now if we switch to time domain, then the analogs of the space periodic Hamiltonian are periodically driven system. And now the question is if this periodically driven system can reveal crystalline structure but in the time domain. So now I have to, not concerning the model which I would like to, on the basis on which I would like to present, to show you what I have in mind, we again return to the single particle bouncing on an oscillating mirror. But now, this is still single particle, but now let us consider a general S21 resonance. And what we have then? We have S Floquet eigenstates, which are represented by but S localized wave packets moving along the S21 resonant orbit. And the corresponding quasi-energies are nearly degenerated. And in the limit, when a resonance order goes to infinity, these quasi-energies start forming quasi-energy band. And what is more, we have S Floquet eigenstate, and proper superposition of this S Floquet eigenstates allows us to extract S individual localized wave packets. And these wave packets, when S goes to infinity, becomes analogs of the Vanier states known in the solid state physics, which are localized in crystal sites. And an example of this, so let me show you an example. This is an example for S equal 4. And here there is a single Floquet state plotted in the configuration space for two different times moment. So we see that for S equal 4 we have 4 wave packets, and we can even find at which direction these wave packets are moving in this moment. But the configuration space is not the domain when we can observe crystalline structure. The domain when we can observe crystalline structure is a time domain. If we fix the position in the configuration space, for example, close to the turning point, and ask how the probability for the detection of our particle at this fixed point changes in time, it is periodic, because each wave packet approaches this point periodically and in the same way which is guaranteed by the Floquet theorem. So this is the domain when we can expect crystalline structure. And this conjecture becomes even more obvious when in the description of the system we restrict ourselves to the Hilbert subspace, which is spanned by our S-localized wave packet. Because then, in this subspace, the expression for the quasi-energy of a particle is reduced to the time-binding model, which is known in the solid-state physics. There is J is a tunneling amplitude, and here, in our case, this amplitude is related to the tunneling of a particle between neighboring wave packets, but neighboring in the time domain. There is also longer range tunneling, but it is orders of magnitude weaker, and similarly like in the solid state physics, in the time binding model, they are neglected. So we see that the resonantly driven system can reveal crystalline structure in the time domain, and actually that was also predicted by Guo and co-workers. They consider perturbed harmonic oscillator periodically driven, and they concluded that show that their quasi-energy can form band structure, and they call it phase space crystals. But they didn't realize that this structure actually must be reproduced in the time domain. It was a slightly different approach. Okay. But that's the conjecture, and now let us see that some non-trivial solid-state phases can be realized in the time domain. Let me start with the Anderson localization. Standard Anderson localization is related to the localization of a particle in the to the exponential localization of a particle in the configuration space due to the presence of the time-independent disorder potential. There is also Anderson localization is also possible in the momentum space, and then it is related to the quantum suppression of classical diffusion of classically chaotic system. But now let me show you that the Anderson localization can be also observed in the time domain. So we have our particle bouncing on an oscillating mirror. We consider very high resonance. And now, on the top of this periodic motion of the mirror, let us add some weak fluctuations. So that let us add perturbation, which is still periodic, but with very long period, with the period equal S times the period of the mirror oscillations. But between the moment 0 and S times the period of the mirror oscillation, it fluctuates randomly. The presence of these perturbations results in additional terms in our expression for the quasi-energy of our particle in this Hilbert subspace, and that terms introduce disorder in the system, and we basically end up with the Anderson model. And of course, Anderson localization is possible. And here there is an example for S equal 4. Again, we fix the position in the configuration space, and we see that the probability for the detection of our particle at this point is exponentially localized around a certain time moment, and this behavior is repeated periodically. Now, maybe it is a good point to compare time crystals and space crystals.
AJ squared is AJ dagger AJ, yes? Last term, yes, because it is
Say again.
conventional. It is AJ dagger AJ.
Not dagger, because this is single particle. This is a
This
complex.
is a single particle operator.
Yes, but this is complex conjugation, not the dagger.
These are not creation.
Okay, because this is
These are amplitudes.
This is amplitude. Many body physics in a while. Now, space crystals. If we have one-dimensional space crystals with periodic boundary conditions, and we add disorder to the system, we can observe Anderson localization, which means that if we go around the ring, we observe that the particle is exponentially localized around a certain space point. And of course, if we keep going again and again, we again and again observe this localization. Now, switching to time crystals, we have to exchange time and space. Now we fix the position in the configuration space and ask how the probability for the detection of this particle at this point changes in time. And if there is a Anderson localization, we will observe exponential localization of the probability around a certain time moment. In the case of space crystals, the larger the ring, the larger the space crystal. In the case of this time crystal model, the higher the resonance S, the larger the time crystal. And actually this Anderson localization, I have presented to you with an example of a particle bouncing on an oscillating mirror, but this is a general phenomenon and can be observed in many periodically driven systems. For example, in the solid state physics, of course, we can think that we have space crystal, and then we add disorder potential, and then we observe Anderson localization. But actually, we don't have to start from the periodic potential. We can, from the very beginning, start with the purely disordered potential, characterized with some correlation lengths, and still Anderson localization can take place. And this is the same possible in time domain. We can have a system which is perturbed, and the perturbation is regular in space for fixed time, but disordered in time. And again, Anderson localization in the time domain can be observed. Experimentally, there is a chance maybe it can be measured in the ultra-cold atoms, but also there is a chance that it could be measured also in a single atom. If we have a hydrogen atom, and hydrogen atom which is perturbed by fluctuating microwave field, again Anderson localization of an electron along the Kepler orbit can be predicted. And if we are able to put the detector, for example, close to the classical trajectory, for example, close to the nucleus, then the probability for the detection of an electron will be exponentially localized around a certain moment of time. What is more, of course, time is a single degree of freedom, and we cannot, there is no hope to have multi-dimensional time crystal. However, time crystals, model of time crystals that possess properties of three-dimensional space crystal can be invented. And for example, in solid state physics, there is Anderson transition in Anderson localization process, but that requires three-dimensional systems. And we have shown that Anderson localization in time domain can also reveal phase transition. There is an idea how to do it, or also how to see this phase transition also in time domain. All of it was related to a single particle problem. I mean, this in this part of my talk. And now we can return again to the many-body problem. For example, let us again consider ultra-cold atoms bouncing on an oscillating mirror. But now we consider high resonance S, and we consider let us consider repulsive interaction between particles. And then, if we restrict in the description of this many-body system, if we restrict ourselves to the Hilbert subspace spanned by this S-localized wave packet, the many-body system is described in case of the bosons, by the Bose-Hubbard Hamiltonian. And now we have, apart from the kinetic energy term, we have also interaction terms. And if we have interaction terms, then we can ask what is the ground state of this Hamiltonian. In other words, what is the lowest energy state in our Hilbert subspace? And if the interactions are negligible, then of course the ground state is the Bose-Einstein condensate with long time phase coherence. Now, when the interactions are repulsive and sufficiently strong, then the ground states become a single Fock state, and the long time phase coherence is lost, the energy gap is formed, and basically the system behaves like a mod insulator-like state, but in the time domain. Because we would put the detector at the fixed position in the configuration space, we will observe that the well-defined number of particles are approaching our detector like on some conveyor belt or whatever. That's all. Summary. Time crystals are analogs of space crystals, but in the time domain. And we have shown that spontaneous breaking of the discrete time translation symmetry into another discrete time translation symmetry is possible. And this phenomenon was recently observed experimentally. And in the second part of my talk, I considered condensed matter physics in time crystals. And it is standard procedure in solid-state physics that space periodic potential are often used to model properties of space crystals. And it turns out that periodically driven system can do the same, but in the time domain. And I have shown you that Anderson localization and mod insulator-like phase can be also realized in the periodically driven system, basically in the time domain. Thank you very much.
Can this be realized also for harmonic interactions, for harmonic oscillators?
I would expect it could be possible.
Because it's an exactly solved problem. But you didn't try it.
I didn't try, and I expect it is possible, because the integrability it is not the point. We need interactions, and probably it is possible. Mariusz.
I have a comment.
Mhm.
The comment is that close to the end you were showing this example of electron on a Kepler object. I don't like this example because for me the time crystal is really many body problem. It's a situation when you have one particle density which is uniform, but very structured high order correlation function, and order correlation function shows structure, and then you have to break the symmetry, and then you see that this one particle density has the same structure as this high order correlation function. But if you are talking about non-dispersing wave packet or whatever, or single particle, there is no difference between one and many particles, and this is very difficult. So I want to call it
Okay.
time crystal.
So it was.
This is the comment.
But that was exactly the reason why I want you I wanted to warn you that this is a separate problems. In this concerning this Kepler problem, what I consider, if you switch to the solid state physics, this is the same as considering one particle in the periodically especially periodic potential. So and then I ask about the properties, for example, Anderson localization. Nothing to do with the formation of time system. This is a separate, point of view.
So,
Yeah?
so you mean that this time crystal was constructed by some many-body system, and then in this system there is additional
So
particle
impurity
which interacts
time
with this
crystal.
many-body system. You can, like in normal crystals, you have ions which form the crystal, and then you have single electron in this.
Well, yes, one can say so. However, it is not easy to find what is behind of this external periodic force. In the solid-state physics, we know. For example, regarding this Kepler single particle Kepler problem, of course, there is nothing like many-body physics behind this. This is only the analysis of the periodic problem, periodic in time, single particle periodic problem. But there should exist some systems which initially can reveal spontaneous breaking of time translation symmetry and formation of time crystals. And then one can probably reduce the description of the system to this kind of approach, whereas one particle, for example, in the presence of let's say fixed external time-dependent force. Yes? Yes, but because
Can I ask if this
Mariusz was asking.
Yeah, so my question is short. I want to continue. The first part we're talking about experiment. In experiment, they had to introduce some kind of disorder in order to see this.
The tuning. This disorder is other question, but
But in the Hamiltonian when you show, I think that it was. So my question was because in the example with oscillating mirror there was no any disorder. So and this yeah. And is this disorder necessary for observation? Is it something?
yes, this is very good questions, because at the beginning the authors claimed that disorder and many-body localization is necessary in order to prevent the system from heating. But the regime MBL, MBL means many-body localization regime. MBL regime was obtained that experiment, but not in this one. And of course, theoretically, we don't need many-body localization to see spontaneous breaking of time translation symmetry. In my opinion, this presence of this disorder illustrates the robustness of the self-organization process, but this is not necessary ingredient of the problem of the
In
phenomenon.
other words, even without this term, they should see.
Of course, because this is the let's say the physics. Yeah. Yes.
But now they know about your paper, so they try to do it without disorder.
They actually even in this paper they present okay there the problem is that disorder in the experiment is not necessary at all, but the problem is that this is not the thermodynamic limit. So claiming if it is necessary or not basing on this experiment is of course not possible. Here it is a bit better because this is 10 to the 6 particles, but okay. Yeah.
If I have a normal crystal which shows Anderson localization, then I can perform a certain number of purely macroscopic experiments on that crystal, and then I can show what are the consequences of the Anderson localization. Same with mod insulator. Can you tell me what kind of an experiment I can do with your time crystal? Which will but I mean the same because you use the word mod insulator. There is a certain definition what is meant by the insulator. So would
Okay.
that be how can you on this little experiments with 10 ions that should be possible to say, should I add there something or what should I measure?
Okay. Concerning this, for example, Anderson localization in solid-state physics, it is very difficult to see in solid-state material. There is some signature, but clear observation of Anderson localization was observed, for example, in ultra-cold atoms. When they prepare the
That's a question of opinion, what you said.
yeah.
Because the solid state physicists down there in the building will tell you a different story, but let's not discuss that. Okay. So what about the mod insulator?
About mod insulator, for example, in ultra-cold atoms, the mod insulator is detected, for example, by turning off the trap, and after time of light, you don't see the interference.
Time of the crystal, how do you do the
Yes, yeah, but I'm coming to this. Now, if you have, for example, particles moving, that bond insulator means that each wave packet which is moving along the resonant orbit is occupied by a well-defined number of particles, and there is no phase relation between these wave packets. So if you turn off the driving and let the system evolve, after time of light, you would not see any interference, which will be in the contrast as compared to the regime where there is a Bose-Einstein condensate and there is no mod insulator phase. Actually, this is pretty the same strategy can be applied to detect this kind of phases.